Welcome back, my sweet chemists. We are going to be talking about the electromagnetic spectrum, radiation, energy, frequency, wavelength. And this video will go along with activity 1.2.3, which is practice electromagnetic radiation problems. But before we get into that, we need to talk a little bit about some of the formulas we'll use and some of the conversions we're going to use. And the number one, well, there's two equations that we're going to use the most. C, this is our speed of light, and E is going to be energy of an electron, actually of a photon. Okay. So the formula for the speed of light is actually wavelength times frequency. So this one is called the lambda, and this one is called nu, Nu. Energy of electrons of the photon is Planck's constant, which we denote with H, times frequency. So this is Planck's constant, and we're going to use a version of Planck's constant, and of course this is frequency, that's nu. So lambda is wavelength, TH. This is going to be measured in some sort of meters, and then frequency is measured in hertz. A hertz is also a per second. In other words, how many waves pass a certain point per second. That is what a hertz is. C is the speed of light, and it's also a constant. It is going to be 3 times 10 to the 8th meters per second. So obviously that's speed. We have distance over time. Energy of electrons, H, Planck's constant, we're going to say it is 7 times 10 to the negative 34 joules, which is a measure of energy, times seconds. And then obviously our frequency is measured in per second, or hertz. So we're going to have our seconds cancel, leaving joules, and that's the measure of energy. Okay, so those are the two equations that we're going to use. The next thing I want to talk about are the types of conversions that we're going to need. So we're going to have nanometers, we're going to have picometers, we're going to have kilometers, we're going to have gigahertz, it could be a gigameter, anything like that. Let's see, is there another one? I think that was it. So let's look at what those conversions are going to be. So 1 nanometer is equal to 10 to the minus 9 meters. 1 picometer is equal to 10 to the negative 12 meters. 1 kilometer, or kilometer, is equal to essentially 1,000 meters. And then 1 gigahertz, or that gig, is 10 to the 9 hertz, or per seconds. So the big thing here is we need to look at these, what these conversions are. When we're working with the speed, with C and the speed of light, our wavelength must be in meters, must be. When we're working, have anything with frequency, it has to be in hertz. So this has to be in hertz. It has to be. It can't be gigahertz. It can't be picohertz. So we're going to have to do some sort of conversion. I think that is all of the preliminary information. So let's go into the activity. So they're asking us, using the equation and the energy equation. So the wave equation is C equals lambda nu, or wavelength times frequency. The energy equation is Planck's constant times frequency. Derive an equation that expresses photons' energy in terms of its wavelength. So in other words, we want to get wavelength into this energy equation. Well, we've got two equations, and the thing that they have in common is frequency. So if we solve our speed of light equation for frequency, that's going to be speed of light divided by wavelength. Then what we can do in our energy equals Planck's constant times frequency, we can take frequency and substitute it in for that. So then that's going to give us energy equals Planck's constant times the speed of light divided by wavelength. So in this case, we finally have our energy equation in terms of wavelength, not just frequency. The other thing that I do want to talk about is the relationship between energy, wavelength, and frequency. So remember when we were talking about relationships, if two terms or variables are on the same side of an equation, they are indirect. And if they are on opposite, they are direct, right? So what we know is as energy increases, so does frequency, but our wavelength decreases. And if you think about it, if you have a really small wave, that's going to have very high energy. The frequency is very high. It's passing that point a lot of times per second. But the wavelength, the length from one to another, that length between those two waves is very, very short. So that's a short wavelength. On the other hand, if we have a decrease in energy, that means that our frequency is going to decrease. And that means that our wavelength is going to be much bigger. So it'd be something like this. So we're looking at, again, remember it was the wavelength between two waves right here. That's lambda. So the bigger that the wavelength gets, the longer that wave is, the less energy it has, the less frequently it'll pass a point on that wave. So this is how they're related. This is a really important point that you need to make sure you understand. All right, so now let's get into some calculations. So it says calculate the frequency. So we're going to figure out what is our frequency for all of these. And remember, that's called nu, of light that corresponds with the following wavelengths. So these are all wavelengths, and we know that because, well, not only did they tell us, but they're all meters. So these are wavelengths. That's our lambda. This is what our lambda equals. So the equation that corresponds or relates the frequency and wavelength, do you remember? It is C equals lambda nu. So speed of light equals the wavelength times the frequency. But in this case, we're going to solve it for frequency. But before we even do that, we've got to get these wavelengths into meters. They have to be in meters. So using what we talked about at the very beginning, we can use our dimensional analysis, go from nanometers to meters, and it is 10 to the negative 9 meters. That is what one nanometer equals. So if I calculate that out, and I'm going to put it as 2 times 10, I'm moving that decimal twice, so that's going to be at the negative 7 meters. So now that I have my wavelength in meters, I'm going to put it into our equation. So these three little dots mean therefore. We're going to solve our speed of light equation for frequency, which is going to be the speed of light divided by our wavelength in meters. Speed of light is 3 times 10 to the 8th meters per second. I'm going to go ahead and put that in the denominator because that's where it is. Divided by 2 times 10 to the negative 7th meters. So we can see that meters and meters are canceling, and I've got, it's not seconds, it's going to be a per second. So that's a hertz, and that's how we measure frequency, which we know we're on the right track. All right, so let's do our math here. So 3 divided by 2, that's going to be 1.5 times 10. And remember what we do, if you're dividing exponents, we're going to subtract it. Oh, I didn't leave myself very much space, did I? So that's going to be 8 minus a negative 7. So in other words, 8 plus 7. So that's going to be 1.5 times 10 to the 15 hertz, which is a per second. That's a hertz. So this is our answer for that first one. All right, let's move on to the B. We've got our wavelength is 30 picometers. And as you can remember, hopefully, a picometer compared to a meter, so 1 meter is equal to 10 to the negative 12. I just put that in the wrong place. Hold on. I'll get it. Meters. 1 picometer is equal to 10 to the minus 12 meters. All right, so we put that in, let's see, let's move that decimal over, and so instead of 30 we have 3 times 10. Since we moved it one space, it's going to be to the negative 11 meters. Again, because we have, now that's our wavelength, we can put it into our frequency equation. C divided by lambda, speed divided by the wavelength. So 3 times 10 to the 8 meters per second, and divided by 3 times 10 to the negative 11 meters. Again, meters and meters cancel. I've got per seconds. That's good because that's a hertz. Per second is a hertz. I always say that the units will save our acetate. It's chemistry cussing. I'll teach you. So 3 divided by 3 is 1 times 10. And again, we're dividing that, so we're going to subtract it. So that's 8 minus a negative 11. So that's going to be a 19. For a second, so 1 times 10 to the 19 hertz. Box your answer. All right, moving on to C, we're going to see what the frequency is for, this is a big wavelength, 10 kilometer wavelength. It's like a radio wavelength. It's really, really big, or ship to shore. So what we know is that 1,000 meters is equal to 1 kilometer. So let's put that in scientific notation. So 1 times 10 to the 4 meters. So therefore, we're going to put it in our new frequency divided by frequency equals speed of light divided by wavelength, or C divided by lambda. So that's going to be 3 times 10 to the 8th meters per second. And then we'll put our wavelength underneath. So 1 times 10 to the 4 meters. Again, our units cancel, meters and meters. We've got a per second, which is a hertz, that's a good thing because we're trying to figure out frequency. So 3 divided by 1 is 3 times 10 to the 8 minus 4 because we're dividing. So that's going to be 3 times 10 to the 4 hertz. That is not very frequent. Okay, so that is how we are going to calculate frequency, how often a wavelength passes a certain point using wavelength. Make sure that you always have that wavelength in meters. Okay, going on to the next one. This is, we're going to calculate the energy of photons. And we've got different givens. So we know that we need to calculate energy. Energy. We've got one on the, okay, energy down here. So the first one, we've got 350 nanometers. Meters, again, that's going to be wavelength. Gigahertz. Hertz is frequency. So that is frequency. And then down here, we've got centimeters. Meters, again, that's going to be wavelength. So you just have to be aware of which one you're trying to figure out. All right, so let's start with the first one. So we've got 350 nanometers. Remember, we can't do anything until we get it into meters. So let's go ahead and do that. So 10 to the negative 9 meters is equal to 1 nanometer. So that is going to be, let's move that decimal over twice. So 3.5 times 10 to the negative 7 meters. So that's our wavelength. And they're asking us to find energy. So the formula that we're going to use here is not this energy equation. We're going to go ahead and use this one because we've got wavelength. So let's do that one. So therefore, energy equals, come on, Planck's constant. It's really dragging. I don't know what's wrong with it. Hold on. Planck's constant times the speed of light divided by wavelength. It's frozen.